3-2, polynomial functions and their graphs, day 2. Our learning goal is that you will be able to use the intermediate value theorem to show the existence of real zeros and graph the polynomial functions. So let's look at the intermediate value theorem. This theorem tells us the existence of real zeros. So far we've been factoring to find them. But according to this theorem, when you have a graph and you have a point above the x-axis and below, so let's say this point was 1, -5, and this was 2, 7. What this basically means is if this happens, there is a real zero that occurs between those two x, or those 2 points. But the key is one of your y's has to be negative and one has to be positive. So there has to be a sign change in the y values. And if this happens, there is a real zero or an x-intercept between those two x values. So example 1, we're going to use that intermediate value theorem to show that each polynomial has a real zero between the given integers. So the way that the theorem works is you're going to plug in 2 and 3 and show that the y values have a sign change. So first I'm going to plug in f of 2, and then I'm going to plug in f of 3. So I get 16 plus 6 times 8 minus 18 times 4. And then I just use order of operations. 16 plus 48 minus 72. And then I'll get that answer. Let me slide this down. So this is -8. Now I'm going to do f of 3. (81) plus 6 times 27 minus 18 times 9. So I get 81 plus 162 minus 162, which would be 81, and that's plus 0. So if you were looking at a graph, we have 2 and -8 and 3 and 81. So because those y values, one's positive and one's negative, then you've shown that there is a 0 between them. And that's all you have to do because we're not finding it. Okay, now we're going to graph polynomial functions. And when you graph, there are steps you go through. So the first step is to use the leading coefficient test to determine the end behavior. So because this is a negative and even, then it's going to fall left and fall right. B, we're going to find our x-intercepts. And to do that, we have to factor it. So I'm going to take out a negative x squared, and that will leave me with x squared minus 4 equals 0. And I'm going to set each one equal to 0. And I'll factor this further. So here I'm going to get x squared equals 0, dividing by negative 1. So x equals 0. So this is 0, 0, multiplicity of 2. So this is going to touch the x-axis and turn around. This one I have 2, I'm going to have to set equal to 0. So I have x equals negative 2, x equals 2. So this is negative 2, 0, and 2, 0. And both of these have a multiplicity of 1. So that means they're just going to cross the x-axis. Okay, C. Find the y-intercept. You're going to plug in 0 for all the x's. And you're going to get 0. So your y-intercept is 0, 0. Then you're going to find out if this has y-axis symmetry, origin symmetry, or neither. And usually the evens have the y-axis symmetry, but you plug in negatives for all the x's. And we've done this before. And you're going to get negative x to the 4th plus 4x squared. And if you notice, everything stayed the same, so this is y-axis symmetry. Okay, and then E, now we graph it. I'm going to graph it on the next slide. So we're going to use everything that we just calculated to do our graph. So we know on both ends it's going to fall. All right, so we know we have y-axis symmetry. Our x-intercept, we had one at negative 2, 0, 2, 0, and 0, 0. Our y-intercept was also 0, 0. And then you just use your end behavior to help you graph. Now, the number of turning points, so you'll know how many to turn. I should say the least number. The greatest number of turning points. You take your degree, which we represent as n, and you subtract 1. Since our degree was 4, you're going to do 4 minus 1, which is 3. So at most, you have 3 turns in your graph. So just remember that. You can't go over 3. All right, so we're going to start, because remember it falls. And at negative 2, it crosses. Crosses. And then at 0, we do touch and turn. And then back at 2, 0, it crosses. So this was across the x-axis. This was cross the x-axis. And this point we did a touch and turn. And we don't care about the height of these, it's okay for right now. Okay, so we're going to do one more. So we're going to start with A, which is the leading coefficient test. Let's actually make this, we'll keep it positive. So this is, we have 1, 2, 3. It's 3 x's, so this is a positive odd. So remember, positive odds have positive, look like positive slopes. So it's going to fall left and rise right. B, our x-intercepts. So luckily this is already factored. So you're going to set it equal to 0, each factor, and solve for x. So this one's already 0, 0. This one's negative 3, 0, because x equals negative 3. This is x equals 3, so this is 3, 0. And all of these have a multiplicity of 1. So they're all going to cross the x-axis. C, your y-intercept. Remember, you're going to make all the x's 0. So this will be 0 times 3 times negative 3, which equals 0. So it's 0, 0. D, you're going to figure out what kind of symmetry it has. So you're going to plug in negative x for all the x's. Negative so because everything changed, and if you don't know, you can always do this, FOIL this out. And this will give you x cubed minus 9x. Because that'll make it easier. Now let's plug in negative x, negative x. So this is negative x cubed plus 9x. Because everything changed from our original, then this is origin symmetry. And then last, we're going to graph it. Okay, so we have an x-intercept at negative 3, 0, 3, 0, and 0, 0. And our symmetry is, it's going to be diagonal. And we're going to fall left, remember. Now to find the number of turning points, you're going to take your degree, which is 3, and subtract 1. So we can have at most 2 turning points. So here we go. We're going to fall first. Fall, cross, cross. So we only have at most 2 turning points, so we're good. And it's origin symmetry because it's symmetrical over the origin.